Okay, so today, like I mentioned at the end of last session, we're going to talk about don't care conditions in state tables and in their role in K-maps. Let's say you have, let's do a little bit of a background. There is something called BCD. Binary coded decimal, where you want decimal numbers, but you're using binary. The decimal digits can be represented by 4 bits. I'll do and okay, so those are your 16 combinations of 4 bits. Binary coded decimal only uses the first 10. And these are not used. So to represent a decimal number in BCD, binary coded decimal, you would say the year 2026 would be represented by 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0. Just the 4 bits corresponding to each of the corresponding decimal digits. You generally don't do math this way in a computer, but sometimes you have a need for binary coded decimal. Or if you see BCD, this is what it's referring to. Now, with logic circuits, you would have situations where where you don't care what the result is. So, say you want a circuit that does something when a binary coded decimal signal comes in and the number is prime, for example. So you would have your out, your A, B, C, and D. And your out is 0, 0 there, 1, 1, 1, and 1, 0, 0, 0, 0. Those are all the prime numbers for these for a binary coded decimal digit. Now, what the situation? You have these 6 numbers here, that aren't going to come into the circuit. Those numbers are not in the BCD system, so you don't care what these are, what result these have. You don't care. They can be 1 or 0 on the output. It's not going to happen, so it doesn't matter. So you put an X there to indicate that you don't care what the result is. Okay? So when you do the K-map for this, draw out your 16 grid, and 0, 0, 0, 1, 1, 1, 1, 0, and 0, 0, 0, 1, 1, 1, 1, 0. Let me just make sure that this is, you can distinguish the difference there. So 0, 0, 0, 0 is going to be a 0. Let's just do the ones. 0, 0, 1, 0 is a 1. 0, 0, 1, 1 is a 1. 0, 1, 0, 1 is a 1. No, that's a 0, 0, 0, 0. And 0, 1, 1, 1 is a 1. Okay? And then you have these, the 1, 0, 1, 0 is an X. 1, 0, 1, 1. 1, 0, 1, 1 is an X. 1, 1, 0, 0 is an X. 1, 1, 0, 1 is an X. 1, 1, 1, 0 is an X. And 1, 1, 1, 1 is an X. All right. So the rest of these are zeros. So you can have your groups that you create can have X's in them or ones. And you could easily do the two groups like here, this group and this group. But those are going to have 3 terms each. That would be, what is that? Let me do the, let's see here, C and C prime and D and D prime. And this one would be A and A prime and B, B prime. So you would have C, B prime, C, A prime. No. What would this group be? C? B prime, A prime. Yeah, that's right. A prime, B prime, C. And this group would be B, A prime, or A prime B, D. Okay, so 6 literals and 2 terms. But with the x's there, you can make it a little bit more simple. You can make groups of 4, 2 groups of 4, 1 group here, and 1 group here. And that would be C, or B prime C, and D, BD. Because you're including the x's in the terms. Functionally, if all that's coming in are BCD signals, functionally these two are the same. But the second one is going to be easier to implement because you're taking into account don't care situations. Because the don't cares could be either ones or zeros depending on what you want them to be. So, yeah. Where are you guys at in the lab at this point?
Lab 5.
Lab 5?
Yeah, but he's making it hybrid now, so he hasn't really, he learned like hybrid.
Okay. But what was Lab 5 supposed to be? Is that Boolean algebra?
Yeah.
Okay. It's been a while since I taught digital logic lab, so I'm trying to remember the labs in the order. So you haven't gotten to K-maps yet in the lab. Okay, good. As long as I'm staying ahead of the lab, we're good. But let's see here. Yeah, you can use don't care conditions to make more simple circuits. This is just one example of where it might be used. You could change this to be whoops. Yeah. If you want even numbers to come through, and odd numbers to be 0, You could do something like that. And then do the K-map appropriately. Yeah, don't care conditions. This is one of those situations where some teachers and even engineers refer to this as a truth table. It's actually properly called a state table, like I've been trying to use consistently through the semester, because truth tables have two states. There's this third state of don't care in this that could represent either state. Truth tables don't have a don't care state. So this would be a state table. Let's see here. Let's go ahead and do this one with the odd number or the even numbers. Let's see here. And that's A prime, B prime, and that's C prime, C and D prime. All right, let's get some help from the audience. Where's the first one go? Here? Okay. The next one? 0, 0, 1, 1, 0. Let's see here. 0, 1, 0, 0. 1, 0, 1, 1, 0. And 1, 0, 0, 0. Now the x's. You do the x's, you do the ones first and the x's second. And then fill in the rest with zeros. So 1, 0, 1, 0 is an x. We had this before, so I should have left them. 1, 0, 1, 1. 1, 1, 0, 0. And 1, 1, 0, 1. 1, 1, 1, 0. And 1, 1, 1, 1. Oh, this is easy. Just one term, right? Do you see it? What's the one? What's the one term? What's the one group? Yeah, the X's are don't care, and because they can't with a binary coded decimal, these are not possible. So it doesn't matter what the output is, because the inputs will never get to that point. Okay. So what's the so what's the one term? Just one group of 8. It wraps around, remember? So the one term would be D prime. A and A prime doesn't matter. C and C prime don't matter. B and B prime, both of them work. So it'd just be all the ones and all the ones and some of the X's are in D prime. Simple as that. So X's and ones. I forgot to put the zeros in here. X's and ones to group together. To make the most reduced expression. Let's look at one from a perspective that I'll probably put on the quiz for this section. Let's see here. Do a sum of 0, 1, 3, 5, 7. Now, from this, what can you tell about the function? How many variables can does it have? Well, the number of variables is the number of inputs is input combinations is 2 to the n power, right? N being the number of inputs. That's the number of combinations, right? So what power of 2 includes all these? 3, because it's less than 8. All the terms are less than 8. So equals f of A, B, C. All right. So you can tell that this has 3 inputs, and you do A, B, C. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And what's the binary values of each of these numbers in the sum here? What's the binary values of these numbers? You got 0, which is 0, 0, 0, 0, or 0, 0, 0. 1 is 0, 0, 1. 3, 0, 1, 1. 5, 1, 0, 1. And 7, 1, 1, 1. And that could be grouped together how? The group of 4, yeah. Oh. And the upper left hand too, yeah. All right. Which gives us the expression. Let's see here. This is B and B prime and C. Yeah, C prime. That's A and A prime. So, so would the final expression be? No, I'm sorry. This is backwards. A and A prime. There we go. So, what would the expression be? Mm-hmm. Or C. Yeah. There you go. Now, keep in mind that this could be also written, the equivalent function would be what, 2, 4, 6? In products, in product form, you would put the numbers where the zeros are. These are equivalent. And if you have both, you might reveal a don't care condition or two. So, for example, let's see, let's say you have sum of 0, 1, 4, 6, 7, 9, 11, 14. And the product of 2, 5, 8, 10, 13, 15. Where's the 12? Don't care. If this, do this out in the K-map, you have, this is 4 variables, so W, X, Y, Z. Okay, so you have a 1 and the 0. 1 here. 4 would be 0, 1, 0, 0, right? 6 would be 0, 1, 1, 0. 7 would be 0, 1, 1, 1. 9 is 1, 0, 0, 1. 11 is 1, 0, 1, 1. And 14 is 1, 1, 1, 0. Now the zeros from the product here, you would have 0, 1, 0, 0, 1, 0. 0, 1, 0, 1 for 5. 1, 0, 1, 0, 0, 0 for 8. 10 is 1, 0, 1, 0. 13 is 1, 1, 0, 1. And 15 is 1, 1, 1, 1. And these are don't cares. If you go through them, you'll see that 3 is missing and 12 is missing. So to satisfy both of these, you could do a group of 4 here, a group of 4 here, and group of 2 here, and group of 2 here. So go with what's missing to be the don't cares, and make your groups accordingly. So, yeah, that's the usefulness of don't cares. You can create larger groups and reduce the number of literals used in a expression. So I don't know if you're going to run into this anywhere where you get both the sum and the product expressions written out like that, but this is how you would deal with it if you did. So I unfortunately forgot to bring my textbook with me, so I don't remember offhand what comes next, but that should be the basics of K-maps. We'll probably have a quiz on K-maps next Thursday. Tuesday we'll move on to start on the next subject. In the meantime, have a good day. See you on Tuesday.